solutions to this assignment here quickly, and then we'll go straight to questions from you guys. So for number 1, I got x squared plus 2x minus 15 plus 2 over x plus 2. For number 2, I got x squared plus x minus 12 with no remainder at all there. For 3, I got 2x to the 4th minus 19x to the 3rd plus 13x squared plus 139x plus 105 with no remainder there. Hi. For 4, I got just x minus 5. So notice this problem wouldn't work real well if we had a remainder here, but on each step of this division, I'm getting remainder 0 the whole way through. And you can see the slick little setup I did with my synthetic divisions where I just used the result of the previous synthetic division as the inputs for the next step. Kind of a sneaky way of setting that up. For 5, I get 2x minus 3 times 4x squared plus 6x plus 9. For 6, I got x squared minus 5 times x squared plus 2. For 7, I got x plus 2 times x squared minus 7. For 8, I got x minus 2 times x plus 2 times x squared plus 4. For number 9, I have x cubed minus 7 times x cubed plus 5. Bless you. You're welcome. For 10, I got 3x plus 4 times x minus 3 times x plus 3. For number 11, I got x minus 2 times x squared plus 2x plus 4 times x plus 2 times x squared minus 2x plus 4. For 13, I got 2x plus 3, x minus 2, and x plus 2. For 14, I got 2x minus 1 times 4x squared plus 2x plus 1 times x minus 2 times x squared plus 2x plus 4. And then the last one, I got x to the 4th plus 16 times x squared plus 4 times x plus 2 times x minus 2. And if you want to look at my work further, this is posted on PowerSchool. If you go to the calendar and you find this assignment, you'll see this answer key posted with the printout for the assignment if you wanted to go and take a closer look at anything I did. But we'll also take questions right now too. So you guys ready to do some questions then?
I think we're ready.
I'm ready. Let's do this. What do you want to start with? Anybody at all? Can I do the whole front?
we start with
Yeah, we do 3.
3? Sure. That's from the front. That's kind of a compromise, right?
Yeah.
Okay. All right. So first thing we should observe is that if I look at the divisor, although it's degree 1, its leading coefficient isn't 1. So I can't use synthetic division the way it's currently written. So I'm going to do the long division. So I set it up by putting the divisor on the outside, and then the dividend goes under the division bar. And this one, although it looks pretty gross, everything works out pretty neatly. The numbers are maybe a little bit large, but the process, nothing weird kind of happens. Okay. So I start by asking myself the question, what times 3x gives me x to the 5th? I did not mean to get rid of the 6. That's very important that that's there. Thank you. All right. What times 3x gives me 6x to the 5th? So I need a 2, because 2 times 3 is going to give me 6. And then what power of x do I need? X to the 4th, because x to the 4th times x to the 1st is x to the 5th. So I multiply that to both terms in the divisor. And then we're going to subtract that down. So 6x to the 5th minus 6x to the 5th is 0. Negative 47x to the 4th minus 10x to the 4th is negative 57x to the 4th. And then we'll bring down that next term. And I ask myself, okay, what times 3x gives me negative 57x to the 4th? Well, clearly it has to be negative, right? And if I take 57 and I divide it by 3, I get 19. So it's going to be 19. And then the x part, what power of x do I need? To the 3rd, because x to the 3rd times x to the 1st is going to give me the x to the 4th. So I multiply that to both terms. So I get 57x to the 4th. And negative 19 times 45 is negative 95. And then I subtract down. So negative 57x to the 4th minus a negative 57x to the 4th just gives me 0. And then negative 56x to the 3rd minus a negative 95x to the 3rd is just like negative 56 plus 95. So when I do that, I get, what, 39x to the 3rd? And then I bring my next guy down. And I repeat and I say, okay, what times 3x gives me 39x squared? Well, it's got to be 13x squared, right? Is everybody okay there? So I multiply that to both pieces, and I'm going to get 39x cubed plus, what is that, 65x squared. And I subtract down. So 39x cubed minus 39x cubed is 0. 482x squared minus 65x squared is 417x squared. And then I'll bring down the next piece. And then I'll ask myself, okay, what times 3x gives me 417x squared? Well, 417 divided by 3, if I type that into my calculator, I get 139. And then what power of x do I need? Just x to the first. So if I go and I multiply that to each term of the divisor, I get 417x squared plus 695x. Obviously, I type those into my calculator. I'm not doing that in my head. I mean, I guess I could if I really wanted to, but like, nobody really wants to do that. So, what do we got then? So we do 417x squared minus 417x squared is 0. 1010 minus 65 is 315. And then I'll bring my last number down. So this will be the last time I have to do anything. So then I'll ask myself, okay, what times 3x gives me 315x? If I take 315 and I divide it by 3, I get 105. And 105 times 3x is just going to give me exactly what I need, right? So if I distribute that to both terms of the divisor, I get 315x plus 525. And when I subtract that, I obviously get 0. And I'm done. So my answer there is just what we've written here. And since it's remainder 0, I don't have to worry anything about writing plus the remainder over the divisor, right? So big picture, what does this mean if I get remainder 0 when I do one of these polynomial divisions? Well, let's relate this back to numbers, right? If I do 6 divided by 2, that gives me a remainder 0, right? What can I say about the relationship of 6 and 2? Well, I'd say 6 is divisible by 2, right? As opposed to if I said 6 divided by 5, that gives me a remainder 1. I would not say 6 is divisible by 5. Everybody agree with that? Furthermore, if a number divides another number, we know that that number is a factor of it, right? So I can write 6 as the product of 2 times something else, whatever that quotient is. Similarly here, the polynomial 6x to the 5th minus 47x to the 4th, yada, yada, yada. One of the factors of that polynomial is 3x plus 5. So if I try to factor that big polynomial, it's going to be 3x plus 5 times some other polynomial. Specifically, what will that polynomial be? It'll be the quotient to this problem, the 2x to the 4th minus 19x cubed, yada, yada, yada. And this is what we're going to be working on in the next chapter when we talk about factoring and solving polynomials in general. We're going to be using that technique that, hey, if I can divide one polynomial by another and get remainder 0, I know that's one of the factors. And if I can kind of figure out what would be a good thing to divide by, I can start peeling off the factors and end up with a factored polynomial by using division to do that. And we'll look at that more here in the coming chapter. But that's why I've emphasized some of this division pieces right now, is we've spent much more time on the division operation than any of the other polynomial operations, mostly because we have an application coming for polynomial division here quickly, that takes really, full advantage of these division techniques, specifically the synthetic division, which is makes these problems pretty fast if you're able to do synthetic division. Now, did anybody try to think of a way that we can do 3 by using synthetic division? So we can do a little bit of a modification to make synthetic division work if this is still a degree 1 divisor, even if the leading coefficient is 1, but it takes a little bit of extra work. So what I can do is I can factor off a 3. Everybody kind of see what I did there, where I just factored out the 3. If I look at this piece that remains, that's a degree 1 with leading coefficient 1, right? So I should be able to do synthetic division with this. And in fact, we can. Let's just do that on the side here. Now, as a word of warning, notice there's a fraction here, so this can get a little inconvenient from a computation standpoint because you have to worry about adding and subtracting fractions and the like, which isn't always super easy to do in our head the way like whole number arithmetic is. But there's no reason I can't do that. Now, we still have to worry a little bit about this 3, but let's see what we get when we do this synthetic division, and then we'll take care of the 3 afterwards. Everybody's okay with that plan? Okay. So I bring the 6 down. When I multiply negative 5/3 times 6, what do I get? Hi, Michael. I get negative 10, right? 6 times negative 5/3 is negative 30 over 3, which reduces down to negative 10. Everybody's okay with that? So if I add down, I get negative 57. Okay. If I do negative 5/3 times negative 57, what do I get there? I think I get 95. And if I add down, I get here 39. Bless you. And negative 5/3 times 39 is negative 65. And if I add down there, I get 417. Negative 5/3 times 417 is, what is that going to be? 130. Negative 695. And I add down, I get 315. And negative 5/3 times 315 is negative 525, which gives me my remainder 0. Everybody's okay with that? Now, maybe the fractional arithmetic there, you would have wanted to use your calculator to handle, and that's fine. You could certainly do that. In this case, all the multiplications come out to be whole numbers, which is rather handy. It makes this problem much less of a bear than if you got like fractionals, you know, like a fraction is your answer for the multiplications. So that's nice. So we've divided by this piece. What haven't we divided by, though, yet? The 3. So all I'm going to do now is just divide each of these guys by 3. And if you look and compare this to the answer that we got up here, what do you notice? It's exactly the same, right? It did end up working. Now, took a little bit more effort. I had to muck around with some fractions when doing my synthetic division. I had to remember to go back and then divide that, the coefficient back off at the end, but you can do it that way. Now, as a word of warning, if this problem had a remainder on it, you're going to get a boatload of fractions doing it that way, and it's going to get kind of nasty, potentially. But to be honest with you, the long division might have gotten kind of nasty too. So, but that's reasonable to do, is we kind of made that problem into something we could use synthetic division on.
So if there's a remainder, you still probably.
You'd have to divide the remainder by 3 also, yes. Yeah. That's an interesting question. Hold on, I have to think about that for a moment. Yes. Yeah, I think, yes, I do believe so. But that's a nice workaround to still take a problem that at a first glance needs to be done using long division and still kind of make that synthetic division process work for you. Which again, much quicker. Now this one, it was quite convenient. It's a possibility that could become really inconvenient and you'd get a lot of fractions to have to deal with. But I think even if you did the long division, you'd be getting a lot of fractions to deal with there as well. So it's probably not any worse off. But that's a nice little modification there. Now, my intention would be that nobody probably thought to do this. But this is why I put this problem on there. So it gave us the opportunity to talk about this little trick. Okay? All right. What else do you guys want to talk about? It was your guys' assignment. I already know how to do all this. You know, I need to know from... Potentially. Yeah, we're rounding in. I think today we'll probably finish the last topic that I want to cover on this part of polynomials. We have a lot more polynomial things to talk about, but I think this is kind of the natural divider between the two halves of this polynomial topics and makes a good point to make a test at. We'd probably start it now and then we'd review at the beginning and then test the next semester, and it would end up being a semester 2 exam topic or whatever, but that's probably how I would sort that, because I'm not in a rush to try to cram a 6th test into this first semester. 5 is a very good sampling of your guys' abilities.
So are we just going to do this?
I would probably do it during the week, and we'll just find something else to do during the final time. You guys probably would be happier to have this course kind of done with, more or less, and not have to worry about a test during that finals periods. Not a midterm. Okay? And that's probably what I would rather do also. I think you'd be better suited to do it while it's fresh, and then we'll do something fun, or I'll do something for extra credit or something, we'll do something like that. It would be on the last final exam day, yes. So the only exam, you'd have 8th period after this, whatever your 8th period exam is.
I thought they were going one day.
I know.
So on Monday, I think it's a regular schedule, and then on Tuesday it's 7 to 8. finishing classes, community time, lunch, exams, 1 and 2.
Yeah.
What? Yeah. So, yeah, ask me. Oh, I have it.
So that's kind of what the end of our semester looks like. So this will be, this test here of this topics that we're working on right now will be the last test in the first semester. Fair enough? Okay. All right. Do you want to talk about any of these factoring problems? Of course I can do 10. All right. So if we look at number 10, when I'm going to factor one of these, what's the first thing I need to look at to determine how I want to factor this? I have to look at the number of terms. How many terms does this polynomial have? 4. So if I'm going to be able to factor it, I'm going to have to use grouping. Everybody agree with that? So what's the one catch that we have to remember when doing the factoring by grouping? We have to have a plus sign in the middle of the two groups. So rather than thinking about that as minus 27x, I'm going to think about it as plus a negative 27x. That was probably the hang up there if I were to take a guess, Jack. Okay, so from there, in the first group, I'm going to look for a greatest common factor. What's the greatest common factor between 3x cubed and 4x squared? X squared. So when I factor that off, I'm left with 3x plus 4. And in the other group, negative 27x minus 36, what's the greatest common factor there? You can do more than negative 3, negative 9. So when I factor that off, I'm left with 3x plus 4. And now if I look at this in totality and look for a greatest common factor, we see the 3x plus 4 is in common to both terms. And that leaves us then, when we factor that off, with x squared minus 9. And now I have to keep going. I have to check these factors and see if any of those are factorable. 3x plus 4, not going to be factorable because it's degree 1. The second one, though, is factorable. That's a difference of 2 squares. So should be easy to see that x squared is x squared and 3 squared is 9. So I can just write that as x plus 3, x minus 3. And then I'm done. You guys okay on that? Jack, did that?
Yeah.
Was it the negative thing?
I don't know.
Okay. Yeah, sure. Just curious. That's why I included this problem, is so that you had to remember, to give us a good opportunity to remind about that, having to have a plus sign between the two groups, because it's easy to forget that. And it certainly will not work out if you didn't do that. So we got to be careful on those. Who else has one here? Sure. Okay. So first thing I need to check is the number of terms. How many terms does this polynomial have? 3. So for a 3-term polynomial, it needs to be in the quadratic form. So then that's the next thing I'm going to check. Is this in the quadratic form? Yes, I have a degree 6, followed by a degree 3, followed by a degree 0. So that definitely fits. Okay? So if this is factorable, I'm going to be able to factor it like a quadratic. So I'm going to say let y equal x cubed. Remember, I always set y to be the variable from the middle term. So when I do that substitution, I get 8y minus 65y, or I'm sorry, 8y squared minus 65y plus 8. And now what I have is something expressly quadratic. Note here the leading coefficient for this quadratic is not 1. So I'm going to have to do the longer factoring on this. So what I'm going to need to do is find the two numbers that multiply to give me 8 times 8, and then add to give me negative 65. Hopefully it's not hard to see that those two numbers are going to be negative 64 and negative 1. So what I do with those two numbers then is I'm going to replace the negative 65y with negative 64y plus a negative 1y. And now I'm going to factor this by grouping. From the first group, I can take out an 8y. And the second group, I can take out a negative 1. And if I look at this in totality, I can take out a y minus 8, leaving me with 8y minus 1. But I didn't want to factor this over y's. I wanted to factor it over x's. So I'm going to go ahead and put my x's back in. And now I need to check to see if either of these factors I can factor some more. Well, I notice right away that x cubed minus 8 is a difference of 2 cubes, right? It's x cubed minus 2 cubed. And 8x cubed minus 1 is also a difference of 2 cubes, because I have 2x cubed minus 1 cubed. So when I apply my difference of two cubes formula to the first one, I get x minus 2 times x squared plus 2 times x plus 2 squared. And when I apply that same formula to the second piece, I get 2x minus 1 times 2x squared. So that's 2x times 2x, or 4x squared. Plus 2x times 1 plus 1 squared. Okay with that one, Jack? So that was a lot to do there, right? We had a bunch of factoring to do. There were several layers we had to kind of work through. But if we, like that's probably about as bad as it can get, right? Where you have the long quadratic factoring followed by more factoring for each of the factors, right? Okay. Any last questions today? Okay. The next topic we're going to talk about builds directly on top of this factoring technique. Today what we're going to talk about is solving a polynomial. So let's say, for example, we wanted to solve this one for number 10 that we just worked out. So the first thing we have to do is make sure it's equal to 0. The beginning step to solving any polynomial is it has to equal 0. This should remind us very much of solving a quadratic, right? So I go ahead and I do the factoring exactly like we did. And once I have this thing completely factored, I can apply the zero product property. And that allows me to set each of these three factors equal to 0. And now I can solve each factor independently. So for the first factor, I can subtract 4 from both sides and then divide by 3. For the second factor, I can subtract 3 from both sides. And the third factor, I can add 3 to both sides. So my answer would be -4/3, -3, and +3. So not much to add on here at the end, right? It's very much the factoring being the hardest part. We also factored 14. Let's solve 14. Okay, so let's pretend that this was a solving problem and it said equal to 0. So we do the factoring the exact same way. And once we have our answer in factored form, then we can take each of the factors and set them equal to 0. Everybody's okay with what I did there? Now, 2 of these are very easy to solve. X minus 2 equal to 0, I can just add 2 to both sides. And 2x minus 1 equal to 0, I can add 1 and then divide by 2 to both sides. And those answers I get almost without having to really think about anything. How am I going to have to solve x squared plus 2x plus 4 equal to 0? I do not want to subtract 4 from both sides. What kind of equation is this? This is a quadratic, right? So what are the different ways we had to solve a quadratic? We could factor, but is that factorable anymore? No, that one doesn't factor anymore, so that option is out. What's the other best option? We can use the quadratic formula. That always works for a quadratic in standard form, which is exactly what we have here, right? So x equals -b plus or minus square root b squared minus 4ac all over 2 times a. 2 squared is 4, and 4 times 1 times 4 is 16. 4 minus 16 is -12, and 2 times 1 is 2. What happens when I have a negative underneath a square root like that? Well, how do I get rid of the negative underneath the square root? Oh, guys. No one? We need to use an I, right? We're getting an imaginary answer. You guys remember doing this from chapter 3? Some of us more than others, maybe. Okay. And now I could do a little bit better simplifying this. This answer would be fine for you guys, but we can simplify this a little more. Just FYI, this would not be what your calculator would give you if you tried to run the quadratic program that we wrote. Because we can simplify the square root of 12. Remember that 12 is 4 times 3? So the square root of 12 is the square root of 4 times the square root of 3. And the square root of 4 is just 2. Now notice everything in the numerator has being multiplied by 2. So I can reduce that. And write my answer this way. That would be your best answer, although I would still take the step 2 above with the square root of 12 in it still. All right, how would I solve the 4x squared plus 2x plus 1? Guys, how would I solve this? We don't know what it doesn't have, we don't know what x equals yet. No, 4x squared plus 2x plus 1. I would not subtract 1. This is, what kind of an equation is this? Quadratic. So how would I solve this? I would use the quadratic formula again. Yes. So I can say x equals negative b plus or minus square root b squared minus 4 times a times c all over 2 times a. Now notice here the numerator is going to be negative 2 plus or minus 4 squared minus 16, or I'm sorry, 2 squared minus 16. The numerator is exactly the same as what we had in the previous one, right? Everybody can see that? So I'm going to go and just go straight all the way to here because we already did that simplifying in the previous one. I don't need to do it again. Over 8. Now notice everything in the numerator is divisible by 2, and the denominator is also divisible by 2. So I can reduce that down into a best answer of that. Negative 1 plus or minus I root 3 over 4. What do you guys think? So the hardest part about the solving is really getting the factoring done correctly. The worst thing that can happen is you have to deal with solving some of these quadratics, which is why back in chapter 3, I was really wanted to make sure that we went back and relearned those topics if we didn't do very well on our chapter 3 test, because this solving of a quadratic is something that happens over and over and over and over again. Yes, Christian? Of course. So it'll happen here frequently in this chapter, and really like, I don't know, probably 2 or 3 other chapters in second semester, we end up having to solve quadratics inside of other problems.